Welcome, everyone. My name is Dr. Michael Larson. I am looking forward to talking with you today on this symposium on rigor, reproducibility, and impact of psychophysiological research. We're going to talk about statistical power, different research pipelines, reliability, and open access advantages. Pleased to have with us Dr. Kaylee Carbine, Dr. Peter Clayson, and Harold Roca, one of the graduate students working with Dr. Clayson at the University of South Florida. I'm going to share my screen here. And I just wanted to introduce the symposium briefly and talk about why what we're doing is important. So replication is considered the bedrock of scientific practices. It's been said that replication differentiates science from pseudoscience. Yet, as we all know, there have been multiple instances of studies not replicating in the literature. This may be due to a number of things, but one of the primary things is the pattern of incentives in science. People are encouraged to get research out as quickly as they can, to try and publish novel findings as quickly as they are able in order to, whether it's getting tenure and promotion or receiving grants, that can lead to a number of different questionable research practices in an attempt to find positive results. Some of these questionable research practices can include, but aren't limited to, things reported in an anonymous survey of 6,000 American Psychological Association members. They included a large number of people who didn't report all the dependent variables that were collected, only reporting the ones that produce significant effects. Other individuals stopping data collection after multiple times looking in order to see when they reach statistical significance. Others report unexpected results as if they were previously hypothesized, a practice known as harking, or hypothesizing after the results are known. Others omit negative findings, or say they're pilot studies, or say they're methodologically flawed, while positive findings they accept with little or no scrutiny. And a small percentage, but far too high in my opinion, admit to even fabricating data. So these questionable research practices can influence the findings that are out there and can certainly lead to failures to replicate. This emphasis on innovation, emphasis on positive results and speed of publication often results in things that are difficult scientifically to replicate. Other difficulties include low statistical power, small sample sizes, flexibility in analyses that are conducted, or data collection rules, changing stop rules, changing sample sizes, multiple examinations of the data statistically, a practice often known as p-hacking, or the garden of forking paths where people make multiple analytic decisions along the way. And in addition, reviewers and editors often ask for clean and tidy results, which really aren't the case in many scientific studies, where the reality is just more messy. So in the end, this publish or perish culture pushes for flexible analytics, high volume of output that can encourage questionable research practices that ends up with a failure to replicate. One of my favorite quotes comes from Brian Nosek and his group. And he says essentially that incentives for individual success are focused on getting it published, not on getting it right. And that's something that we feel is important to change to ensure the replicability of our results so that they can have a more accurate and beneficial impact. In 2017, Dr. Scott Baldwin provided a nice article in the International Journal of Psychophysiology that included 6 ideas for improving psychophysiological research in order to increase the replicability of our results. First, he said that we should report sample size information. That includes stop rules and how we calculated our sample sizes. Dr. Carbine's going to speak quite a bit on this today. Second is he said that we need to increase sample sizes through collaboration. This is something that's happening throughout the field and something we can all continue to do better. Third, pre-registration and registered reports to decrease analytic flexibility. Fourth is improving reporting standards. In other words, following established guidelines. There are some great papers out there, and the relative number of people following these guidelines is much smaller than we'd expect, and that can cause some difficulties. Similarly, we want to increase the transparency of the pipelines that we're using during our data analysis, and Harold Roca is going to be speaking quite a bit on that today. We also want to shift those incentives. We want to try to improve how we're measuring in our departments for tenure, promotion, for grants, reviewers, editors across the board so that we're focused more on getting it right than just simply getting it published. And finally, we want to improve measurement so that we're more accurately reporting reliability and decreasing the error in our measurement. And Dr. Clayson's going to talk about that today. So the current symposium is focusing on many of those ideas that Dr. Baldwin put forward. First, Dr. Kaylee Carbine is going to review some of the sample sizes and statistical power information that we've seen in the EEG ERP literature. And her talk really highlights the impact of small samples and the importance of calculating sample size calculations a priori. Second, Harold Roca is going to talk about the ERP processing multiverse because there's so many pipelines we can use. In fact, in the study he's going to talk about, there were over 3,400 different pipeline combinations. And he's going to emphasize some of the importance of data processing choices and analyzing the multiverse to improve our consistency and replicability in our research. Dr. Peter Clayson is going to talk about the error that's often in our EEG and ERP research that's rarely accounted for, and that the reliability is often unreported. He's going to talk about a tool that's available called the ERA Reliability Toolbox that allows for reliability estimates and reporting of numbers of trials included in our research to help improve rigor and data quality. Finally, I'll wrap up by talking about the open access advantage and how open transparency in our publishing practices can benefit both the field as well as the individual researchers. So we're pleased to have these researchers with us. We hope you enjoy the symposium, and I'll now turn the time over to Dr. Carbine.
Thank you. I'm excited to get us started and to kick this off. As was mentioned, I'm going to be talking about the issues we see with small samples and how that leads to low statistical power in our EEG and ERP research. Before I begin, I'd like to quickly thank the funding sources and my collaborators for the help that they did on these projects, because wouldn't have been possible without them. And one of the small but many things that I've had to adjust to over the past 18 months is not being able to have samples when I go into an ice cream shop or parlor, gelato stand, whatever it is. And I'm the person you would have hated to have in front of you because I wanted to try all the flavors. I wanted to make sure that whatever one I ended up with was the perfect flavor, the best flavor out there. And so now that I don't get to sample, it's pretty much guesswork. I just have to make a choice and hope that that was the right one. And I honestly don't even know if it was because I don't have anything to compare it to. And as small of a concern as this is in the scheme of things, it actually has a really nice parallel to our issues with sampling in research. If we are able to have large enough sample sizes to do a lot of sampling, then the results we get back, the effects we get back are going to be representative of that true effect, the one true effect. However, if you limit your samples, then it pretty much becomes guesswork, and what you get back may or may not reflect the true effect that's there in the field. And so that's why I really want to talk about small sample sizes and how they lead to low power. And we see this across many scientific disciplines. And when we have this low power, it leads to something that's called type M, or magnitude error, which is when the effect that you observe is going to be a different size than what the true effect is in the population, or a type S error, which is a sign error, which is when the effect that you observe is actually going in the opposite direction of what the true effect is. And with our low power and having these type M and type S errors, we're going to have a low probability of replication in the field. There's going to be an increase in the number of false findings, and this is all going to come together to lead to contradictions in the published literature, which is a problem because we then aren't able to move forward as a field and discover what the true effect is. So one of the solutions, while we will talk in the symposium about many solutions to improve the rigor of science, a solution specifically targeted at this issue of small sample sizes and low power is conducting a priori sample size calculations, where based off your analyses and the size of the effect you want to detect, you can figure out how many participants you need. And this makes sure that not only are studies sufficiently powered to detect true effects, it will reduce the number of false findings, it'll make sure our effects are not inflated, help with those contradictions we see in the literature, and allow us to keep moving forward as a field. So with that all in mind, we wanted to assess kind of where we are in the EEG and ERP field with this. First, looking at barriers we have, particularly in published literature, that might be preventing us from ensuring that we're adequately powered to detect effects of interest. And looking specifically on if we're actually conducting a priori sample size calculations, and are we reporting the necessary parameters that are needed for others to conduct a priori sample size calculations. And then looking and seeing, is this even a concern in the field? Like, what is our average sample size? What's the typical power that we see? Is this something we are struggling with? And then finally, looking at some application to contradictions we've seen in the literature and how low power might be contributing to those contradictions. And I'm going to be doing this over a series of 3 studies that we've conducted over the past couple of years. So first, looking at, are we even conducting these a priori sample size calculations? Are we reporting the necessary parameters? What we did is we took 6 highly cited EEG journals in 2016, did a random selection of 100 studies from those journals, and had 2 raters that looked simply at, is there an a priori sample size calculation being reported? And then are the parameters that are needed for future a priori sample size calculations being reported as well? Specifically, are the correlations or variances among repeated measures being reported? Are test statistics with their degrees of freedom being reported? Are means and standard deviations of the EEG and ERP values being reported? And then of course, are effect sizes being reported? And what we found was not great. So spoiler alert. We found that no studies out of those 100 conducted an a priori sample size calculation. And 2 of those studies actually came from the lab I was in when we did this. And so this is when we hang our head in shame that we weren't doing these things that we know now can definitely improve our research. And for studies that did the repeated measures type of studies, none of them reported any correlations or variances among repeated measures as well. 93% did report a test statistic, but only 56% reported mean EEG and ERP values, and only 47% reported standard deviations or standard errors, which is important because especially when you're calculating sample size, doing sample size calculations, the means are pretty useless if you don't have the standard deviations or the standard errors as well. And then only 40% reported the effect sizes. So really, this just shows we're not doing sample size calculations or helping ourselves in being able to conduct future sample size calculations. And so the next step was then to see, although we're not doing these a priori sample size calculations, what are our average sample sizes? What is our typical power? Like maybe this isn't as big of a concern. And so what we did for this was we took the top 3 ranking journals in the neuroscience, neuropsychology field, plus the 2 flagship journals for EEG and ERP research. So Psychophysiology and the International Journal of Psychophysiology. And over a course of 6 years, we selected 5 studies or 5 papers from each journal for each year. So we had 150 articles. And we again had 2 raters who recorded what the final sample size was for those articles. And then with those final sample sizes, we conducted power estimates for a paired sample t-test and a 2 within by a 2 between group ANOVA. And the reason we focused on these specific analyses is because we also recorded what analysis people used to test their hypothesis. And by far, the most common was a paired samples or version of paired samples t-test and a 2 within by 2 between group ANOVA. As a note, we had 78 different models actually that were used in those papers. Some of them had 5 factors, some of those factors had like 50 levels in them. So there were some pretty complicated statistical designs, but we again focused on these more simple ones that tended to be the most common. And we found when we looked at just sample sizes that overall, on average, the articles had about 29 participants in their studies. But when we consider groups, since we are going to be looking at some analyses that have group levels in them, there were about 21 individuals per group. So we took this 21 sample size forward as we conducted our power estimates and basically went to see with this sample size, what size of an effect are we actually powered to detect in the literature? And the results aren't super happy as well. For a paired samples t-test, for 80%, with a sample size of 21 individuals, we're powered at 80% to detect a Cohen's d of 0.64, which is a medium to large size. And for a 2 within by 2 between interaction, we're powered to detect a Cohen's f of 0.44, which is a large effect size. So really the takeaway here is that with our sample size of having 21 individuals in a group, we're only powered at 80%, which is an adequate level of power, what you want to achieve, to detect only really large effects and nothing else. We took this one step further and want to know if we were interested in more medium or small effect sizes, how many participants would we need for these models? And we found, as you can see on the chart here, that for a small effect, you would need well over 100, even over 200, almost 300 participants, depending on the type of analysis you ran. For a medium-sized effect, that number is a little bit more manageable, but we're still needing about 50 participants in a group to detect medium-sized effects. So our average sample size of 21 really isn't cutting it. And if we want to be adequately powered to detect medium effects, we need at least 50 individuals per group and well over 100 if we want to look at small effects. So a lot of this isn't very happy news. So we're not conducting the a priori sample size calculations. We're not really powered to detect anything but large effects. And so we wanted to see how do we see this maybe applying to the current literature and the contradictions that we see. And there was a meta-analysis that came out that looked at the relationship between the error-related negativity, or the ERN, and depression, and the reward positivity, or RUP, and depression. And it found that the effects for the relationships between these ERPs and depression are very heterogeneous. They're going in different directions, there are different sizes of effects, it's very inconsistent. And so what we wanted to do is we want to look at that research area and conduct a P-curve analysis, which is when you take the significant findings from a group of studies that are all looking at some similar goal, and you plot the p-values from those significant statistical tests, and based off the distribution of those p-values, you can make some assumptions about the data. Specifically, if it looks like results were being selectively reported, is there evidence that there is a true effect in these studies? And also you can get an estimate of what the effect size and power is for those studies. And so what we did is we had 2 raters again, who used that meta-analysis and did an updated literature search. And we recorded the hypotheses in the studies they had to be, testing the relationship between these ERPs and depression, and then the significant statistical tests that supported that hypothesis. And what we found was that both the ERN and the RUP did show some weak evidence or weak support for relationship with depression. And the reason I say weak is because part of doing P-curves is you'll drop the smallest p-value kind of as a sensitivity measure to see if results hold. And when we did that for both of these ERPs, the results became inconclusive, kind of suggesting that it's really hard to actually determine if there's a true effect going on here or not. And what's really interesting is if you take that forward and look at the effect sizes and the power of those studies, both the ERN and the RUP, the estimated effect size was a medium size effect, but the power to detect that effect was only 20% for the ERN and 27% for the RUP, much lower than the 80% that we need. And so it really goes to show that part of the reason we might be getting contradictory research, inconclusive results, weak evidence is because the studies we are using to test those effects are significantly underpowered. And so taking this all together, e.g. ERP research, we're not conducting a priori sample size calculations. We're not reporting the information to help with those sample size calculations. Our research is underpowered, and it's probably leading to these inconclusive or weak or inconsistent findings. So none of this is really happy, not a great way maybe to kick off the symposium, but I want to end on a hopeful note. Other fields are struggling with this as well. It's not just the ERP, EEG research field, but as attention has been brought to it, other fields have been able to increase their a priori sample size calculations, therefore making sure their studies are powered enough to detect true effects and helping improve the rigor of their fields. And we absolutely can do the same thing, that as we collect larger samples, conduct those a priori sample size calculations, report information that will help others do those sample size calculations, we'll make sure that we're powered enough to detect true effects, just like you want to make sure you get your true favorite flavor of ice cream. Thank you.
All right. Okay. Hello, everyone. Today, I'm going to talk to you about how to make more informed decisions about data processing parameters so that we can improve the quality of our data and ultimately the replicability of our findings. You can think of this as a sort of roadmap to optimizing the data processing pipeline. I'll be explaining this approach using, as an example, a recent analysis of ERN data collected by my advisor, Peter Clayson, with Dr. Baldwin and Michael Larson. But first, I should address, well, what do I mean when I say optimizing data processing? Well, as we know, when processing any kind of information, we need to make decisions about what we consider a signal of interest and what is just background noise. Let's imagine that you have a very fancy camera. If you're taking a picture of flowers in a field, for example, there are a number of decisions you can make about how to adjust your camera to collect what you're looking for. You might, for instance, adjust the focus of your camera so that just one part of the flower is in focus, or you could find a way of capturing all the background as well, in which case, like, the whole arrangement of the plant is what we call the signal. You can heighten or lessen the exposure so that the pictures are brighter or darker. In all cases, you're still collecting information about the same flower. However, the decisions you make about focal length, exposure, or any number of parameters you set will drastically impact what information is most salient in the photo. You might want something different for a magazine than for a botany textbook. In ERP work, the signal we're interested in is typically the ERP waveform, of course, but this waveform can be optimized during processing in terms of a number of factors. In other words, we can maximize certain attributes of the ERPs, such as data quality. Data quality could be when we have an experiment and we're interested in looking at participants' general response to a task. We want each trial to look similar. For data quality, we could try to reduce the between trial standard deviation by having very strict eye correction procedures, a strong high pass filter, these things that help make the variance between trials as small as possible. That way, we're not capturing all the nuances about what the participant was doing trial by trial. We're capturing a stereotypical response. We can also optimize based on experimental effects. If we have two conditions and we expect that a waveform should occur in one condition but not the other, or if we expect that the waveform should be, the peak should be larger in one condition than the other, then we want the difference between conditions to be as large as possible. For optimizing effects, we can look at getting the largest amplitudes possible for the condition of interest, or the largest difference scores or effect sizes with something like a t-test. There are other facets of ERP data that can be optimized as well, such as psychometric reliability. But for now, I'll stick to using data quality and experiment effects as my two main examples for our purposes today. It can be hard to know ahead of time how we will process EEG data before looking at the data, but making decisions reactively after looking at it can introduce experimenter bias, as Dr. Larson was mentioning. This can make findings less reproducible. If you think back to our photography metaphor, professional photographers don't just tick the same settings every time they take a photo. They adjust to their environments and their creative aspirations to make a truly unique photograph. But probably no one else can ever perfectly replicate the photos they take. Our efforts can be compared to inventing an easy-to-use point-and-click camera that allows us to come up with more or less the same images with the same amount of information in them each time and across many users. This is because while a 1 in a million photograph might be considered a work of art, an ERP finding that no one else can replicate is not so great. So what can we do? Here is a typical processing pipeline for an ERP, such as the ERN. Each blue box represents a decision that we are forced to make one way or the other. There are a number of different filters we can apply, eye movement correction algorithms, reference electrodes, etc. And it's not clear ahead of time how to set them to eventually arrive at our optimal measures of ERP amplitudes. The question that we're faced with is, what's the best approach? The parameters we choose are often inherited from older studies in the lab or based on reviews of the literature regarding the ERP of interest. These are not necessarily the best choices, and sometimes that information is not readily available as is. Also, the choices we make are just one possible set out of many choices. You can think of each set of parameters as a universe within the multiverse of possible decisions. So to look at this multiverse of decisions, we used multi-level models to estimate the effect of each data processing choice on participant level average amplitude scores and the standard deviation scores. One major benefit of this approach is that it allows the data itself to tell us how to adjust the settings. And this is code anyone can run. These models were fit in the R package LME4, and marginal means were estimated using EM means. Our code for taking this approach is readily available on the Open Science Framework by following the link here in the top right. So our analysis of the ERN data looked something like this. As you can see here, we looked at 21 possible options across 7 processing steps, which resulted in 1,728 unique branches of possibility for each condition. Across correct and error trials, that's double that amount, so that's 3,456 data points per participant. I should note here that the parameters we chose were not even extensive, and there are many other approaches to cleaning and quantifying the data that we did not analyze. Still, the ones we chose are fairly common, and future analyses can cover what we've missed. Now I want to show you the waveforms that resulted from all of these different approaches, just to give you a sense of how they varied. So the data we collected was from a modified flanker task. We ran 298 participants. On the right, you can see the time course data for error trials and correct trials. Each color that you see is a different contingency, and it might be hard to see that there are more than 1,700 of them. If they had resulted in identical waveforms, this would suggest that the parameters we select for data processing didn't matter. However, altogether, you have some spread across both conditions. What we're interested in is actually the difference between these two conditions to characterize the effect of error versus correct response. Now here we have the difference waveform that we get from subtracting one time course from the other. Here also, we see some contingencies that show greater effects than others. You can see that for some colors, the peak and troughs of these curves are smaller and some are larger. In some cases, these disparities are statistically significant. Here I'm showing you the pipeline we tested that optimally maximized the size of the ERN and also the experimental effect of error versus correct response. The items in gray are parameters that were either suboptimal, or in the cases of these over here, the ones that didn't yield a significant difference one way or another. For example, for optimizing the average ERN amplitude, the high-pass filter mattered, but the low-pass did not. Ideally, for getting the largest ERN, we have a mild high-pass filter, a linked mastoid reference, a distant baseline window. We draw our data from a sensor cluster based around a region of interest, and we do directly measure the peak amplitude as opposed to using a mean or relative peak. As a caveat here, I should say that the multiverse analysis approach can only give us exactly what we ask for. A maximal effect size does not mean that this is the truest representation of the ERN. Using a peak amplitude measure, for example, may be benefiting from noise in the time course data that, say, a mean amplitude measure would not. We may have other motives for choosing these parameters than maximizing experimental effects, and ultimately, researcher judgment is still very important. And depending on what you're choosing to optimize, these parameters will change. For example, if we optimize for minimal trial-by-trial variation, the case is a bit different. Here, we've optimized data quality by finding the conditions that minimized standard deviation between trials within participant. Toward this end, all processing steps had a significant impact, and the ideal parameters are a bit different. For example, while a distant baseline window might yield stronger effects, analyses using a baseline close to the start of the trial seem to yield more reliable measurements between trials. So this kind of fine-tuning may prove useful for a number of applications. In clinical work, for example, maximizing data quality within participant can help in characterizing individual differences in neural activity for participants belonging to psychopathological groups that are notoriously heterogeneous. Also, the multi-level models themselves can be useful for future power analyses and add specificity to what samples are necessary for producing a given effect for a set of data processing parameters. So just to review, the steps I recommend you to take home with you are the following. Choose an ERP of interest. Figure out what the different data processing steps are that you have to deliberate on. Try out our code on OSF for looking at all of them, and see which filters and sensors give you the best effect sizes, data quality, or whatever else is your main goal in your studies. Finally, share this work with the community so that we can all benefit from knowing a bit more about what to expect from our ERPs, and so that we can take some of the guesswork out of analyzing them. And while your approach to data processing may become less and less like a unique work of art, it will certainly help us to better understand our place in the vast and mysterious ERP multiverse. Thank you for listening. I'm excited to be sharing this with you. Please feel free to check out a preprint of our paper by following the link here. And with that, I'll hand you over to my advisor, Dr. Reproducibility.
All right, well, thank you all for listening to our symposium today. I want to start off by showing where this talk fits in with the broader open science movement. So the open science movement has a number of components, and the spirit of open science is about increasing transparency and the availability of materials at each step of the process. I want to point out that these components are not mutually exclusive, and I'm going to be focusing on two: open data and open tools. So I want to talk about how we can be more open about our psychophysiological data and about an open tool I've developed to help us do so. So let's consider our hypothetical researcher here. She could be interested in performance monitoring during a Stroop task, collect data on a number of participants, end up with files and files of these wavy lines, and then end up with this beautiful grand average waveform over here on the right. Now, there are a number of data processing steps that go into this process, and Harold Rocha just talked about a number of those. I want to talk a bit more about what goes into data for an individual participant. So here I'm showing 6 individual ERN trials, error-related negativity. I have amplitude on the y-axis with negative plotted down, and time on the x-axis. The time window in which we see ERN typically is shaded there in gray. As you can see from any given trial, it's harder or easier, depending on the trial, to pick out ERN. We score the time window mean amplitude, and we can end up with a histogram of single trial means. And we average them together to get our estimate of ERN for a person, because we assume that on any given ERN trial is some true ERN signal, then some random background noise that just randomly averages out. And that's how we end up with a pretty interpretable single subject average. So for these 69 error trials, we end up with an average score of negative 1.9, and we can do something with that number. The issue is it's hard to characterize data from all trials, from all participants with a single number. So one way we can characterize data from a given participant, characterize a person's data quality, is by estimating the between trial standard deviations. The issue with data quality metrics is they don't always provide information about whether data quality is high enough for a particular purpose. So for that, we have internal consistency, which scales data quality by between person differences. So you could imagine a situation in which we have low internal consistency and we just have a clump of participants, and we can't distinguish those participants with our ERP scores. When internal consistency is high, we can distinguish participants. Our data quality is high enough to look at between person differences. So I've brought up data quality and internal consistency as ways we can open up our data about the quality of our data and about whether they're good enough for studies of individual differences. And I want to focus a little more on psychometric reliability because it's important and its potential impact on statistical inferences. So poor reliability can lead to the misrepresentation of effects. So we can end up with magnitude errors, which are too big or too small than what would be expected in the population, or sign errors. So maybe our patients are looking better than our controls, but in truth, our control should be performing better than our patients. Poor psychometric reliability can lead to reductions in statistical power, can lead to failures to find replicable effects, and poor psychometric reliability compromises validity. So these are a number of reasons on why it's so important to understand the psychometric reliability of our data for statistical inferences. There are also a number of practical reasons. First off, there's momentum in the ERP and fMRI literature to start reporting the psychometric reliability of our neural measurements. So at the very least, there's peer pressure to report psychometric reliability. Reliability is also context specific. We can't demonstrate the psychometric reliability of an ERP and one sample and assume it generalizes across samples or even across paradigms that use that same ERP. Very practically speaking, journals are starting to care. So journals like the International Journal of Psychophysiology, journals like Psychophysiology, journals we care about, are encouraging researchers to report the psychometric internal consistency of all of their measurements used in studies of individual differences. So psychometric reliability is important to examine on a study-by-study basis for all of these reasons. And I want to talk a little bit more about how psychometric internal consistency can impact our statistical inferences to set the stage for why it's so important to evaluate it. So I'm going to show you some data from patients and controls. On the y-axis, I'll have between group effect sizes. And on the x-axis, I'll have estimates of internal consistency. So for this data set, I've randomly resampled 10,000 times the number of trials needed to obtain a given threshold of internal consistency. The solid line there is the point estimate for each 10,000 subsample. The dark gray line is the 95% confidence interval, and the light shaded line is the range of estimates. That dotted line there, we're going to consider our true effect size. That's the effect size estimate when we include all trials from the participants. So I think what is most visually striking about this figure is the positive slope of that solid line. As internal consistency increases, the effect size increases and gets closer to the true effect size. Another interesting characteristic, I think, is that the range of effect size estimates constricts or decreases as internal consistency increases. So what's going on when internal consistency is low? We can observe effect sizes that are too small compared to what we would observe in truth. We also can see effect sizes that are too big. So remember, that background noise is random and someone wins the lottery. So some researcher just got lucky, observed effect size that was larger than what would be expected of the population. Another interesting feature, I've added a orange line there that indicates a 0. So when the sign flips, this is that instance when patients look better than our controls, when in reality, our controls should be performing better than our patients. What I think is so beautiful about this figure is that we see these issues all for the same reason: low psychometric internal consistency. And the reason why I focused on between group effect sizes is because psychometric internal consistency still reflects data quality. So it can still be important to report, not just in studies of individual differences, but also in studies of between group effects. So I have a favorite measurement theory for estimating psychometric reliability, and I think it has a number of important advantages for psychophysiologists. So it can handle multiple sources of error, such as different groups, events, numbers of trials, the interactions between those things. It's a very flexible framework that can be adapted to our purposes, and it handles unbalanced data really well. So you don't have to truncate the data set and exclude information in order to estimate a coefficient alpha. You don't have to split the data set in any way, which can lead to biased variance estimates in order to get a split half reliability. Generalizability theory can use all trials from all participants. Of course, with advantages, there are also disadvantages to generalizability theory. It requires a lot more math. Because of this flexibility, formulas have to be developed for each application of this theory. And the software availability for estimating generalizability theory coefficients is quite limited. So I've tried to do something about these two disadvantages by developing the ERP reliability analysis toolbox. And I'll come back to those in a moment. I want to talk a bit more about why generalizability theory is so advantageous for psychophysiologists and how flexible it is. So above and beyond simple internal consistency estimates, it can do test-retest reliability. It can do the internal consistency of difference scores. You can even get subject level reliability coefficients. So I want to talk a little bit more about difference scores and subject level reliability, because I think they really illustrate the strength of generalizability theory. So I'm going to show you data from the same participants. On the top row, we'll have their error-related negativity trials. On the bottom row, we'll have the reward positivity. So ERN and reward positivity both show strong between condition differences in the sample. ERN to each individual event shows great internal consistency. Reward positivity to each individual event shows great internal consistency. These ERPs look pretty good. What matters for difference score reliability is the covariation, or the correlation between the ERP to each individual trial. On the top, we can see here that the correlation between correct and error ERN trials is modest, about 0.3. For reward positivity, it's much larger, 0.75. And that has a huge impact on difference score reliability. So for ERN, that modest correlation, we still observe an internal consistency estimate of 0.8 for the difference score. For reward positivity, it's unacceptably low, about 0.5. And I think this is important to show because I think the common lore about difference scores is that they're inherently unreliable. But that's just not true. They're like any other measurement we use in many regards. We don't know their internal consistency until we look. And difference scores are very popular among psychophysiologists because we're interested in isolating neural activity related to, for example, error processing. Generalizability theory can also be used to estimate subject level reliability. So as I talked about before, it's hard to characterize all trials from all participants using a single metric. The danger of using a single group level reliability metric is that we are masking low reliability in some participants. So generalizability theory can use person-specific error variance estimates, as well as a person-owned number of trials to calculate a person-specific internal consistency estimate. And I want to show a plot of these person-specific internal consistency estimates. So this is from a sizable sample. Each dot represents the point estimate for internal consistency for a particular person. The bars represent the 95 confidence interval, and that dotted line represents the group level reliability, 0.86. When the confidence intervals are black, we're going to consider that those participants are well characterized by that group level estimate, because the group level estimate is contained within their person-specific confidence interval. Those participants in blue and red were mischaracterized by the group level reliability coefficient. Their confidence interval did not contain it. So we're particularly concerned about those participants with reliability that was below the group level estimate. So typically how I use group level estimates in my own research is I estimate the number of trials I need to obtain a group level reliability estimate, and I exclude participants with fewer trials than that cutoff. For this particular data set, there are about 7 to 78 error trials, and the group level estimate could have led us to exclude participants with fewer than, say, 10 trials. That person there in red has a person-specific reliability estimate of 0.5 and had 20 error trials. So using my standard practice approach would have led to that person's data being included. So this shows how the subject level reliability estimates can help pinpoint those participants who have error variances that are just too big, despite having maybe a decent number of error trials. So generalizability theory is very flexible and can handle these person-specific estimates to tell us a little bit more about each participant and whether their data quality are high enough for studies of individual differences. So I've developed the ERP Reliability Analysis Toolbox, which is an open tool to help you open your data. It uses generalizability theory within MATLAB. It's universal. It just reads in single trial scores. And it works for really any trial-wise estimate, not just ERPs. And it will provide you with a number of types of reliability that are useful for ERP researchers. So moving forward, to be clear, I would be delighted if people reported any psychometric reliability estimate. I think generalizability theory has a number of strengths for ERP researchers, but any estimate of reliability will do. I'm just happy when people include them. There are a number of reliability standards that have been put out there. I've advocated for some thresholds myself. Apparently this group, we like Brian Nosek, because I also have a quote from Brian Nosek, that the rules of statistical inference have no empathy for how hard it is to acquire the data. So I'm not going to advocate for any particular threshold. I'll just try to suggest that internal consistency matters. It can lead to compromised statistical inferences, and we need to know what our data look like. We need to open them up. Reliability is also context specific. We can't demonstrate reliability in a single sample and assume it generalizes to similar samples or the same ERP in different populations, or even the same ERP across different paradigms. We don't know until we check. Psychometric reliability is the property of data in hand. It's not the property of an ERP. So to help ERP researchers use generalizability theory, I developed this open tool, the ERP Reliability Analysis Toolbox. I've included a link to this toolbox at the bottom left. And with that, I want to thank my collaborators, my graduate student, and you all for your attention.
I don't know about y'all, I'm having a great time. This is fantastic. It's fun to see people trying to improve data, improve the openness, the quality of everything that we're seeing, and providing very useful tools. So excellent talks. thus far, and it's fun to be a part of this for me, along with these excellent scientists that I'm working with. One thing that I failed to mention in my opening comments was that we have an open science framework page for these presentations. So that open science framework page is going to include copies of the slides that we're presenting, as well as other information and links to papers as well, where we publish some of these data. And so you can go to that open science framework page. You can see it, the osf.io QVZSC there, and you can see everything that's happening. And we're trying to practice what we preach here and as being as open and transparent as we can. So with that, then I'd like to jump into a talk seeing some of the benefits of open practices. And sometimes we like to conflate rigor with openness. And I think there's a reason for that, because when people can examine your data, can look directly at what you're doing, there is a heightened sense of responsibility, and people do tend to go in more rigorous directions when their data are open. In addition, we can see that there's advantages both for science as well as for individual researchers when data are open and available. Now, before jumping too far into this talk, I do need to disclose that I am the editor-in-chief of the International Journal of Psychophysiology. The reason this matters is because the International Journal of Psychophysiology espouses some of the open practices that I'm going to talk about here, as well as a hybrid model where they get increased funding. So it's important to know that I am the editor-in-chief of that journal. So with that in mind, what is open access? Well, open access refers to providing online scientific content that's free of charge to the reader and free of most or some copyright or licensing restrictions. This can include a number of things. It can include data, it can include manuscripts, it can include study stimuli. All sorts of different things can be provided in an open and transparent manner to try and improve the accessibility of our science as well as the quality of our science. And this is needed for a number of reasons. The primary reason is that science is typically a closed off practice. Research findings are often disseminated in journal articles and conference papers that have high subscription fees. Subsequently, only libraries or other research tanks with high funding levels are able to pay the fees for these subscription-based journals. This leads to an inherent inequity. Individuals are unable then to have the information that they want. Low-income countries are unable, or people with less privilege are unable to see science that should benefit us all. In other words, people can't get past the paywall in order to see and benefit from the scientific practices we're engaging in. In addition, research isn't being disseminated. We're not able to implement the findings that are there because they're hidden behind a paywall or because costs are too high. So open access is necessary, and we should be participating and trying to participate, if for no other reason than simply trying to improve the accessibility and equitability of scientific practices. So how do we participate in open access as a researcher? Well, there tend to be two main routes. Ultimately, there are many, but there are really two main routes. You have the gold route and you have the green route. In the gold route, what you're going to be doing is identifying a reputable journal, oftentimes an open access journal, where you'll send your paper for peer review. When the paper is accepted, you'll likely pay an article processing charge, or APC, and then your paper is published in that open access journal. Some of the most common open access journals you've probably heard of, the Frontier series, PLOS ONE. I mean, there are several out there. There are different levels of reputation for open access journals that you should look into closely before you choose one. But the idea that you can publish your findings, that they can be accessible to anyone, is very nice. The con here is that it turns the cost back on you as the researcher. You are paying an article processing charge for the study to be published in an open way so that anyone can access it. So that's the primary gold route. Another route that's also considered a gold route because it costs is a journal that's more of a hybrid model. So I mentioned PLOS or Frontiers as being a primary gold route, as being an open access journal with those article processing charge. Other journals, like the International Journal of Psychophysiology, many journals are what are called hybrid access journals, where they're a typically subscription-only access journal, then you can go in and you can pay an additional open access fee, an additional article processing charge to have your article published in the subscription-based journal and then have anyone be able to access it. So for example, if I were to publish a study in the International Journal of Psychophysiology and I wanted it to be open access, I would have the paper, submit it for peer review, it would be accepted, then I would pay an extra fee in order for the article to be open. So essentially there's a double dipping process that occurs. Whereas libraries, other institutions are paying for the subscription fees, then there's an additional charge for that article, and it's on an article level to become open access. So these hybrid access are also considered to be gold because they're requiring those extra article processing charges. The alternative to these gold routes is the green route. In the green route, you submit your journal or you submit your paper to whatever journal you select, but before you enter the peer review process, you post what is called a preprint. There are many different preprint servers out there: SciArchive, BioArchive, Zenodo, Databrary, and there are many of these different types of pre-processing or preprint servers where you then upload the preprint. And most journals in their copyright guidelines, so long as they have not yet typeset and copy edited, your article will allow for these to be posted. So it is not the final published version, rather it is the final submitted version that you put up. And the text can be the same, the figures can be the same, so long as it has not yet been typeset or copy edited by the journal. This green route is typically free. It doesn't come with those article processing charges. They're typically just for the copy editing and then dissemination. So you can post these things for free. Google picks them up. Anyone can find your article via Google or other search engines. They just typically aren't posted on something like PubMed, where there's more of a journal-specific data repository process. So in short, the green versus gold open access. In green open access, it may not be immediately available due to publisher embargoes. Some publishers require 6 months or a year after publication before it can be posted. But in most cases, it is free. It is immediately available. And you do have to pay attention to copyright rules. So you have to look at when, where, and what version of the paper can be made open access. So sometimes this is ignored by researchers, but it's important that you look. And typically for most copyright guidelines, for example, the International Journal of Psychophysiology, so long as you are not posting the typeset and copyrighted article, you're fine to publish your final version. Gold open access, on the other hand, likely involves those article processing charges, but you do get the advantage of having your final version with all of the typesetting and other things put forward. And so it looks nice and other people can still access it. And it is searchable not only on Google, but also on PubMed and other data search engines. The other advantage of gold open access is it's typically immediately available with reuse rights. In other words, you are signing up for a Creative Commons license for your work, and then others can use it, cite it, and it becomes immediately available to them. So with that in mind, the green versus gold open access, why should we be doing this? So those open access benefits for you as an author aren't always clear. So many of us want to have good contribution to science. We want to ensure that our science is widely disseminated. So it does provide that worldwide audience, but there's also some research that suggests that this can increase the impact of our work, increase opportunities for funding or collaboration with other individuals or other institutions who you may not typically be exposed to. So there may be what we're going to term the open access advantage, where there's increased citations of your work as well as increased exposure to your work. There's also that benefit that I've talked about already to readers and consumers, that there's increased equity, increased availability. And it also makes your data and text available for mining, automated mining, where it can be pulled up by computer processes instead of having to go through paywalls, which increases the availability of data and makes our meta-analyses and other meta-scientific analyses more accurate. So speaking of this open access advantage then, there are many journals listed in the directory of open access. Currently 3,700 plus journals have open access possibilities. There are over 1,280 repositories listed by the Directory of Open Access Repositories. So there are many opportunities here, and there's increasing mandates from the National Institute of Health, National Science Foundation in the United States, the Wellcome Trust in the United Kingdom. Several different funding agencies are increasingly require that the articles be published in an open access manner if they receive funding from their source. This is increasing the frequency of open access type publications. For example, here in a study that was relatively recently published, they showed that 31% of all articles are currently available as open access articles. 52% of current article views are to open access articles, so increase relative to subscription-based articles. And if you look at projected trends, these individuals project that 44% of journal articles will be open access by 2025, and that 70% of article views by the year 2025 will be open access. So there's a big incentive as far as people finding our work to increase the open access publication rates. And these are just the figures depicting that analysis, showing the increase over time in the proportion of views, as well as the type of open access increasing by 2025. Similarly, there's a projected open access, or not just a projected, a real open access citation advantage. You can see here across a number of different journals and publishers. In gray, you can see the citation rates of subscription journals, and in red, you can see the citation rates of open access journals. The red dotted line is the market open access average, and the gray dotted line is the market subscription average. Across these analyses, what these particular researchers showed was increased relative citation rates for open access articles, regardless of publisher, across many journal types. So they've begun to refer to this, as I mentioned earlier, as this open access citation advantage. And they're showing that open access articles have approximately 18% more citations than subscription-based journals across medicine, biology, oncology, psychiatry, but that this is moderated by the impact factor of the journal and the time since publication, as you'd expect. Longer time since publication is associated with higher citation counts. And the open access publication movement has only taken root in the last several years. So many of those older articles that were subscription-based have higher citation counts. But as we move forward toward the present time, we are seeing this continued increase in citations to open access articles. So that leads us to the current study, where we looked at open access specific to human electrophysiology research. We were curious if the open access advantage held for both EEG and ERP research. And these findings are now published in the International Journal of Psychophysiology. You can see the citation information here, and we'll link to this in our open OSF page when we get it completed. So what we did is we took the last 20 years of publications on human electrophysiology research. Our initial data scrape came forward with 35,144 articles across 967 journals. And we wanted to look at four main things. We wanted to look at the frequency of open access publishing in human electrophysiology research. We wanted to look at citation rates, and we used both PubMed and Crossref to have two different metrics of citation rates. Then we wanted to look at alt metrics. Alt metrics are also known as article level metrics, and they include things like internet mentions, blog posts, Twitter mentions, different areas that aren't typically seen in something like PubMed or Crossref that Google Scholar often picks up, but they're considered these article level metrics that are more recent and more internet-based metrics. Then our last goal was to compare green open access articles versus gold open access articles, and to see if there were differences in citation rates and differences in alt metric mentions. So first off, the frequency of open access publishing in human electrophysiology research. Over the last 20 years, there has been a considerable increase in the amount of open access publishing, with 35% of human electrophysiology articles being open access, and those rates increasing considerably over time. You can see here that as we get towards 2019, with the y-axis showing the frequency of open access articles and the x-axis showing the publication year. The black line is showing the open access articles, and you can see the continued gaining of ground over time, with more and more open access articles being published as we move towards 2019 and 2020. The reason for that dip in 2020 is just because of when we gathered the data. The full 2020 articles were not yet available. But you can see in 2019, there was almost no difference in the number of subscription-based articles relative to the number of open access articles in human electrophysiology research. So definitely an increase over time, and approximately 35% over the last 20 years of human electrophysiology articles were open access. As far as citation rates, open access articles showed between 9 and 21% more citations than subscription-based. The 9% was for PubMed, the 21% was for Crossref. So there's a considerable increase in citations relative to subscription-based journals. And this was even more increased, or I should say subscription-based articles. This was even stronger for altmetrics, with open access articles showing 39% more altmetric mentions relative to subscription-based articles. And if you're on Twitter, you can see why this is easy. Many people will simply submit a link to their green open access preprint prior to it even being published, so that they can disseminate the research faster and will also increase their number of mentions overall. Notably, in our analyses, the increased citation rates remained even when we were accounting for time since publication and the impact factor, specifically the 5-year impact factor of the journal. So that open access advantage in citation rates is present, and altmetric mentions, regardless of impact of journal and regardless of time since publication. You can see here just the data that I was talking about: PubMed on the first graph, Crossref on the second, and altmetric mentions on the third. And as I noted previously, altmetric mentions are becoming increasingly popular. And you can see that from 2010 to 2015 in the open access articles and their altmetric mentions. The reason for the decline here in the PubMed and Crossref citations is just simply because time since publication. It takes time for other researchers to find the information and to cite it. But we are seeing an uptick in the amount of open access articles and the citation rates over time. Our final aim was to compare the gold versus green open access models for citation rates and altmetric mentions. So first, for citation rates, we completed a multi-level model looking at these individual articles. And as you can see here, the gold open access and green open access had a 21 or 20% increase in citations relative to subscription-based or closed access articles. For citation counts, there were no differences statistically between gold open access and green open access. In other words, whether you were self-archiving to PsychArchive or BioArchive, or whether it was a International Journal of Psychophysiology type article that was hybrid and made gold open access, didn't matter as far as the amount of increase in the open access advantage. Those were not statistically different. For altmetrics, again, there was a considerable increase. Whether you were open access gold or whether you were open access green, there was an increase in the number of altmetric mentions relative to closed access, but you can see a very strong difference between the two, with an 18% increase for gold open access relative to subscription-based, and a 71% increase in altmetric mentions relative to subscription-based. There was a statistically significant difference between the gold and the green open access as far as altmetric mentions go, with more altmetric mentions for the green open access relative to the gold open access. In other words, there were no differences in citation counts between green and gold models, but as far as altmetrics go, there was a much higher difference, meaning more mentions for the green open access relative to the gold open access. And green open access is typically free to researchers. So shows that, if you're looking for a way to make your article open access, perhaps the green open access model is the best way to do this, so that you are able to have a low cost, disseminate your research well, have a similar citation impact, but have an increased altmetric impact overall. So in conclusion, human electrophysiology research is increasingly adopting open access publishing practice. This open access advantage in citations and altmetric mentions is real and present and will benefit the individual researchers in that way. And as far as green versus gold open access, there are no real differences in the amount of citations, the citation bump, I should say, between gold and green, but the green open access has an increase in altmetric mentions, allowing you to disseminate your research more clearly. I've also included several useful URLs that you can look at, looking at different directories for open access journals, open access news to help you find open access journals that are not predatory in nature, as some are, as well as links to the open science framework and something called Think, Check, Submit that I really like that helps you avoid predatory journals in your quest to try and increase your open access submissions. So that is what we have. Thank you very much. So that was fun. I enjoyed our symposium today. I hope you all enjoyed it as well. We hope that this helps you increase the rigor of your work, the openness of your work, and let you know some new tools and ideas, whether it's the multiverse or whether it's the ERA Reliability Analysis Toolkit, to increase our sample sizes, decrease error, and improve our overall research quality. So thank you for joining us today, and please feel free to jump onto our Open Science Foundation or Open Science Framework page to find our slides and other information there. Thank you.